I may start. Thank you. Yes, got it. So thank you very much for the invitation to speak here. I'm delighted. And as usual, I should start by saying who the collaborators are on this work. So this work is being done in collaboration with my former PhD student, Bowen Chen, with my current PhD student, Dachan Zhang, and with my postdoc, Ricardo Espíndola. And I initially gave the title of two-sided differential entropy. Here you see the title two-sided Crofton formula. And so both of those titles would have been appropriate, and we'll see how that works out in a moment. So what I have to do here is start with a review. And so before we talk about the two-sided differential entropy, or before we talk about a two-sided Crofton formula, we have to remember what the one-sided version was. So this is work that goes back to 2014 or 2013. I had the pleasure of collaborating with Vijay Balasubramanian and with Borun Chowdhury, Jan de Boer, and Michał Heller on this story that I'm about to review for you. And then there was some closely related work by Matt Hedrick, Rob Myers, and Jason Veen. And the question that we studied back then, so this is already 10 years ago, was how to compute the length of a curve in the bulk of an ADS spacetime, and we focused on ADS-free spacetimes from the dual CFT. So in this case, we have the ADS-free CFT2 correspondence. And the reason why we asked that question was that, up until now, a lot of people are definitely excited about the Ryuta-Kayanagi formula, which relates entanglement entropies in the CFT to areas of minimal surfaces in ADS. These are codimension 2 minimal surfaces. So in ADS-free, they would be codimension 2 in 3 dimensions is a one-dimensional object. So minimal areas are just geodesics. So in the ADS-free CFT2 correspondence, the famous Ryuta-Kayanagi formula tells you that the entanglement entropy of a region in a CFT, that would be an interval or a union of intervals, is the length of a geodesic, or possibly a union of geodesics, because geodesics are one-dimensional minimal surfaces in 2 + 1 dimensions. And so the Ryuta-Kayanagi formula in ADS-free CFT2 is a statement about lengths of geodesics. So now it becomes natural to ask, well, what about non-geodesic curves? What if I have a curve which is not a geodesic? Can I compute its length in the bulk of ADS from the CFT perspective? And if so, how do I do it? And we had an expectation that this should be some kind of entropy, simply because the length of the geodesic was von Neumann or an entanglement entropy. And we also had some expectation, which I guess has met with mixed success. But at the time, we thought that this would compute or somehow quantify the amount of UV-IR entanglement in the CFT. Why is that? Because we have the common law that the near asymptotic region in ADS corresponds to the ultraviolet sector of the CFT, whereas the deep interior of ADS corresponds to the infrared of the CFT. So if I draw a curve such as this red curve in front of us, it appears to be dividing ADS spacetime, or an equal slice of it, into the interior, the deep interior and the exterior. That's like dividing the IR of the CFT from the UV of the CFT. And so we also were interested in understanding that. So how do we compute the length of such a curve? Well, if your only tool is the Ryuta-Kayanagi proposal, which is what we had back then, then you have to describe this curve using geodesics, because that's what the RT formula, the Ryuta-Kayanagi formula, knows about. And so we're going to describe this curve through a set of geodesics which are tangent to it. So here I drew a full ADS cylinder. There's an equal time slice. The right-hand side picture highlights an equal time slice of this ADS geometry. And here I have a curve, and I'm describing that curve using geodesics which are tangent to the curve. And each one of those geodesics, here I drew one geodesic, but at different points of the curve, there will be different geodesics tangent to the curve. Each of those geodesics computes the entanglement entropy of one CFT interval. In this case, it's the interval with endpoints U and V. Yes, the whole collection of geodesics which are tangent to the curve, I'm going to describe it with a single function U, which is a function U of V. And the reason why I describe why I have such a function is that, well, yes, I have to describe tangent geodesics, I have to specify. In general, geodesics are specified by two numbers, the left endpoint and the right endpoint of the interval that's being that's being covered by the geodesic. And so we have two endpoints, that's two numbers. If I impose a condition that my geodesic is tangent to the given curve, then that's one condition. So that gives me one functional dependence between U and V. So I express it as a statement that U is a function of V here. So whenever you see U of V from now on, it refers to geodesics which are just tangent to the red curve that I'm trying to study. And the question is, what is the length of this curve? And here is a formula that my collaborators and I back then discovered, which is that the length can be given by the following formula, where S of U of V, which shows up here, is the entanglement entropy. In other words, the length of the geodesic, which covers the interval UV. And it's this specific integrand that's integrated over all of V that gives you the length of the curve. In this formula, I am setting 4g Newton equal to 1. We all know that in the Ryuta-Kayanagi formula, the entropy is equal to area over 4g. I'm ignoring that 1 over 4g factor in this formula. And this boxed formula at the bottom is called differential entropy. So far, I have reviewed for you what we mean by differential entropy. This was a kind of a well-known story 10 years ago, but for the younger people in the audience, or for those who haven't thought about it in 10 years, here's a review. Are there any questions at this point? So until I hear a question, I'm going to end. Please, the moderators, please alert me if there is a question in the chat or something like that. Okay, so this formula there's no other side here. We're just describing lengths of curves in a single ADS geometry. So we're going to add a piece of complication in a moment. But first, I'm going to do something interesting with the formula that we described on the previous slide. So what we're going to do is introduce so here is a copy of the same picture that we saw on the previous slide. And now what I have done is I have drawn an additional auxiliary space, which is called kinematic space. And that space is the space of geodesics in this geometry. Actually, it's the space of oriented geodesics in that geometry. So for example, if I look at a single geodesic like that with endpoints U and V, this corresponds to a single point in that right-hand side geometry whose coordinates are U and V. And these are basically light-like coordinates in this space. So the set of all tangent geodesics is described, as I emphasized on the previous slide, by a single function, U equals U of V. And so I'm having U depend on V in a particular way, and that draws for me a curve through this space, through this kinematic space, the space of geodesics. Each one of the points on the blue locus here, each one of the points in the blue locus here is one geodesic, which is just tangent to the curve on the right. The next thing to say is that this kinematic space here is a space of oriented geodesics. I know which endpoint here is the left endpoint and which endpoint is the right endpoint of the geodesic. So when I draw a geodesic for you, I'm really actually specifying 2 points on the right-hand side. I specify the point u comma v, but at the same time, I also specify the point v comma u. And those points are related in such a way that if I drop a light cone from here, then it will just hit the same bottom points, u and v, at the bottom of this space. So dropping a light cone here takes me to the same place as starting from the blue point or the purple point, and dropping a light cone that way also drops me to the same point over here. So that's the relation between these two points. They are two images of literally the same geodesic with opposite orientations. So why are these things important? The locus here consists, like we said, of the tangent geodesics. The locus here also consists of tangent geodesics, but they are tangent geodesics with the opposite orientation. If you like, we could say that the blue locus here corresponds to or describes tangent geodesics, which cover intervals which are smaller than half of the boundary circle. Whereas these ones, this is the same geodesic, but from the perspective of the other complementary large interval, which covers more than half of the boundary circle. That's one way of saying it. Okay. And now the differential entropy formula, which we saw before, yes, is so I remind you that this is what the formula looks like. It's an integral over tangent geodesics, right? So we could do the integral here on the tangent geodesics, which cover smaller intervals, and compute the length. We can do the integral here on the green locus and also compute the same length, right? Now, we could also combine both of these objects and with multiples with factors of 1/2 and say that the length is equal to half of this differential entropy and half of that differential entropy. Why is this an interesting thing to do? It's an interesting thing to do because now our two integrals, this integral and this integral, form the boundary of a region in kinematic space. And if we have integrals on the boundary of a region, then we can use Stokes' theorem and take the exterior derivative of this integrand to get an integral over the region that lives in between. What is this region that lives in between? I posit to you that this region in kinematic space, the space of geodesics, consists of those geodesics which just intersect my curve. And so this is why I say that the length is equal to, this is the factor, the integral over the locus of those geodesics in this space which just intersect my red curve. That last thing is the Crofton formula, and we have derived it from differential entropy by using Stokes' theorem. And let me just say, why is the locus here, or why is the correct region of integration really given by intersecting geodesics? Well, the boundary of this region is tangent geodesics and tangent geodesics. What is the boundary of the locus of geodesics that intersect the curve? It's the set of geodesics that just barely intersect, but also almost don't. And that's the tangent geodesics. So we see that the region in between the two loci has to consist of precisely the geodesics that intersect my curve. Are there any questions about that? So now this is the Crofton formula. So far still, the story is one-sided. There's no other side to speak of. If there are no questions, then I will go on. So here is something that is dissatisfying about the story that I told you about. The story is 10, or the second slide is like from 8 years ago. This 8, 9, 10-year-old story had one hole, which was always dissatisfying to me, which is that the Stokes theorem derivation we saw on the previous slide, it only works if there is no horizon in the interior of the space-time geometry. Why is that? So you see, we have computed the length of the curve by integrating over these kinds of purple geodesics. That's over here. We have integrated it over these kinds of green geodesics that cover the large intervals, yes, that's here. And then when we use Stokes' theorem, we're saying, oh, now let's integrate everything that lives in between. So that means that we are basically covering all geodesics that I pass through if I deform the purple geodesic to the green geodesic. And I have drawn them here to you with wavy lines. This wavy line, that's one intersecting geodesic. This wavy line, that's another intersecting geodesic. This wavy line, another intersecting geodesic. Each geodesic is a point over here. Now I have a family of geodesics that's a family of points here that just take me from there to there. And we're supposed to integrate over precisely such guys. So that's the physical meaning of the application of Stokes' theorem that we saw on the previous slide. But what happens if there is a horizon? If there is a horizon, there is no way to deform the purple geodesic to the green geodesic in this fashion. Because now I encounter these geodesics that wrap around the horizon of a black hole arbitrarily many times. And so that derivation just does not work. If there is a horizon in the interior of this ADS spacetime, then you cannot interpolate from the smaller intervals to the larger intervals whose covering geodesics are tangent to the curve. Since there's no interpolation, there's no Stokes' theorem to use, and you cannot derive this formula, which is the Crofton formula. And so there's no derivation of Crofton formula that we knew. There was no derivation of the Crofton formula that we knew that would work in the presence of a horizon. So a question that was left over to us from this development, like I said, some 8 years ago, is there, in fact, some Crofton formula when there exists a horizon? And so this is the problem that I will solve for you in the next 45 minutes or so. Are there any questions about that? So far I haven't told you anything new. This is old stuff, like I said, 8 years old or 9 or 10. And
well, I have a question. For this Crofton formula, you need to have this entanglement entropy object S of UV, right?
Yes.
In the presence of a horizon, would you know how to calculate that?
Oh, we would. Well, would I know how to? In many cases, and we know how to calculate it, but we certainly know how to calculate it. Well, if a lot of this work is done with the idea that I believe the Ryuta-Kayanagi formula, maybe because Lewkowicz-Maldacena proved it to me, or maybe I just take it as a tenet. And then if I have access to the bulk geometry, then I can compute it. Now, we are trying to recast a bulk calculation of the length of this curve into boundary terms. So I have to imagine that in principle, I have access to this entanglement entropy. Maybe it's hard to compute, but the field theory knows about it. Maybe it's not easy for me to get there, but it knows about it. So the idea is we're kind of asking an in principle question: what is the quantity in the CFT that knows about the length of a curve in ADS, even if it's hard to compute? And that would be the answer to that.
Thanks.
Yeah. So okay. So far I told you that there is kind of a disconnect because the differential entropy formula, this formula you saw, this doesn't assume that there's no horizon. This formula is fine. But then we can recast this formula into that form using Stokes' theorem, but only if there is no horizon. The moment there is a horizon, I cannot do it. So the question is, can I do something else or something similar, something better, something more general? And I will tell you how in this talk. So eventually we will have a statement that the length of a curve, even in the presence of a horizon, is equal to some integral that looks a little like that. That's what we're going to get. Is that clear what the question is even? I'm not hearing a no, so I assume that it's fine. Okay. So before we go on, I'm going to massage this statement, this formula, not even this formula, the differential entropy formula a little bit. Remember sorry for jumping, but I will jump back to the differential entropy formula. Here it is. It's an integral of this partial derivative of the entropy of an interval with respect to one endpoint, but the other endpoint is being fixed. So, and that thing is being integrated over. So when you integrate that, that's equal to the length of the curve. So what I would like to do now is to discretize this quantity. And remember, we had a quantity where I had a partial derivative with respect to one endpoint, while the other endpoint is being fixed. That's the thing that's being integrated over. In other words, that's the thing that's being summed over. So here I write an expression which looks just like that. For instance, I have A1, because imagine that I have a collection of regions, A1, A2, A3, on a circle. For now, let's imagine that I just have three regions, A1, A2, A3. Then if I write A1, the entropy of A1, A2 minus A1, that's a little bit like taking a derivative of the entropy of a region with respect to where it ends on the right. Does it end at A2 or does it end on A1? Now, it's a very coarse approximation to a derivative, but it's something that looks like a derivative, yes? Now, then because in the differential entropy formula, I need to integrate this kind of quantity, then I add up now similar quantities, removed one over. So I also have A2, A3 minus A3, and A3, A1 minus A1. I hope that my audience will agree with me that this thing is the coarsest possible discretization of the differential entropy formula that we saw on the previous slides. I say the coarsest possible because I have assumed that I have divided the circle not into infinitely many infinitesimal small regions, but literally into just 3 regions. That's very coarse. What if I had divided it into 5 regions? Then I would have written something like this: A1, A2, A3 minus A1, A2, A2, A3, A4 minus A2, A3, A3, A4, A5 minus A3, A4. Here too, I am adding up quantities where the difference between the positive term and the negative term is where I end my interval on the right. That is a discrete version of taking that partial derivative, which was the integrand in differential entropy. So this is the quantity that would be a discretization of the differential entropy formula when I have 5 regions. So now we see, if we compare this expression and that expression, you can see that there will be a pattern. What if I had 7 regions? Then I would say entropy of A1, A2, A3, A4 minus A1, A2, A3. Then A2, A3, A4, A5 minus A2, A3, A4, and so on. So I'm always taking some number of regions minus one less region. And then I add it up over cyclically added up over all the initial points. The A1 is the initial region, here A2 is the initial, here A3 is the initial. This is the kind of quantity that I have to add up to produce a discretization of the differential entropy formula. Are there any questions about that? So the only thing is, so far I have said on this slide is that these expressions form discrete versions of the formula we saw before. So now a question I ask, it's a rhetorical question, I will answer it in a moment, is have we seen these specific combinations of entanglement entropies before? And the answer is yes. We have seen them in the holographic entropy cone program. So I don't know how many people in my audience have followed this program, but in 2015, I will forget some authors, but Seper Nezami, Michael Walter, Hiroshi Oguri, Ning Bao, and Bogdan Stoika, and I think that's all the authors, but I might be forgetting someone, proposed the following problem. They asked, if I have a Ryuta-Kayanagi formula, does just the fact that my entropies obey the Ryuta-Kayanagi formula impose some conditions on the values of the entanglement entropies of a system? And the answer is yes. And if you can find, or in principle, if you knew all such constraints, then you would say that you have solved for the holographic entropy cone. So I'm not going to talk about why it's called a cone and so on. That would be a distraction. But the important thing is that the holographic entropy cone program is the program of finding constraints on the values of von Neumann entropies, which are imposed by the Ryuta-Kayanagi proposal. Or maybe if we can use a different phrasing, if I know that my entropies obey the Ryuta-Kayanagi proposal, then what facts about entanglement entropies can I derive from that assumption? The first such inequality, the first such condition that can be derived, that has been derived from the Ryuta-Kayanagi proposal, is called monogamy of mutual information. We know it, I wrote it for you at the bottom of the page, and I wrote it in a way which just makes contact with my discrete versions of the differential entropy. So you see that here, this quantity there is exactly the same quantity that we are seeing here as our coarsest discretization of differential entropy. So monogamy, and the condition that that's known as the monogamy of mutual information is the statement that this combination has to be greater than the entropy of the combined region A1, A2, A3. So we see that monogamy of mutual information, that specific constraint that had been derived back then, is actually a statement that the coarsest discretization of differential entropy is greater than the entropy of A1, A2, A3. Now, okay. So what I'm going to tell you about today, this is the plan for answering the question that I posed for you before. The question is, can we find a two-sided version of, or can we find a version of the Crofton formula that works even if I have a horizon in the bulk? And here's the way we're going to attack this problem. We first have the statement that the length of a curve is equal to the differential entropy formula. I assume that the curve wraps around the horizon, so it has to be the length of that curve, whatever it is greater than the horizon. This is a simple geometric fact. Now, I have a formula for the length, and if I use Stokes's theorem, then I get the Crofton formula. But I can only do it if there is no horizon. Let's take this expression. So then the question is, what if there is a horizon? Here's the way we're going to solve this problem. We're going to go the long way around through this diagram. First, we take our expression for differential entropy, length equals differential entropy, and we discretize it. That's what we did on the previous slide. We come up with an expression of the form some entropies of regions that are a little bigger minus some entropies that are entropies of some regions which are just a little bit smaller. And we know that those entropies have to be greater than or equal to the entropy of all the A regions because our curve has to wrap around the horizon. The horizon is given by the area of the horizon is the entropy of all the A regions. Now, this is what we saw on the previous slide. We now take this set of inequalities, which we have seen previously in the holographic entropy cone program. So far, I just told you that exactly one of them we have seen before, which is the monogamy of mutual information. But it turns out that more of them have also been discovered in the holographic entropy cone program, and they all look just like differential entropy. Now, what I'm going to tell you about is that my group and my research group have discovered a further generalization of these inequalities. And that further generalization of this inequality is a two-sided generalization. In addition to varying what happens on one asymptotic boundary, suppose that there is a horizon. Behind that horizon, I imagine that there is some purifying system so that I'm dealing with a two-sided black hole. I can now write an inequality of this type, an entropic condition from the holographic entropy cone program that involves both what happens on one side and on the other side. And we have found the relevant valid inequalities that work in this broader context. And it so happens that if you go the opposite way from here, so instead of taking the discretized version, now I take the continuum limit, it turns out that I will get a formula which just computes that length, and this will be the two-sided Crofton formula that we desire. And so this is the plan for answering our question. Are there any questions about what will happen next? This is the plan for the remainder of the talk. So while nobody is saying anything, but if there are questions, then please interrupt me. I will just say, in the first couple of slides, I told you about this box, and then I told you about how Stokes' theorem takes me to here. And then I said, but if there is a horizon, I cannot do it. Then we talked about the discretization of this formula, which takes some form. I will show it to you in a moment. And then what I will do next is to tell you about how this discretized versions of differential entropy formula, they have shown up previously in the holographic entropy cone problem. I will now tell you about how they generalize, and then we will take the continuum limit and we'll see that it just produces the two-sided Crofton formula that we want. So that's the plan. If there are no further questions, then or if there are no questions, then I will keep going. So now we go to typical slides. These were some handwritten slides I prepared, but now we go back to ordinary slides. And when I talked about the plan, I said from here to here, we discretized. That's what we have seen on this slide. Yes, we discretized. And the question is, the thing that we obtained when we discretized, this expression or that expression, I said to you that we have seen these expressions in the holographic entropy cone program. So now let me tell you about what we know about the holographic entropy cone problem, and you will see for yourself that these expressions show up. So at present, the holographic entropy cone program has revealed the following necessary conditions on entropies. If I assume these are entanglement entropies or von Neumann entropies of subsystems, if I assume the Ryuta-Kayanagi proposal. And here's a table. Sometimes when I give this talk or a similar talk, then I ask a question, is my audience, are you impressed or are you disappointed? I think you should be both impressed and disappointed by this table. It's impressive because how did people even find this inequality, you might ask? It looks kind of crazy with all of these coefficients and combinations of terms. On the other hand, you might feel disappointed because people were studying it in order to gain some insight about the Ryuta-Kayanagi formula, but can you really derive insight from such a complicated table? And so some work that I'm not presenting here has actually identified some new insight that we can be gleaned from this table. So in fact, I want to tell you the first thing is that this table actually has a lot of structure. And if you think about it hard enough means on the order of a couple of years, like my collaborators and I have thought about it, then you start to understand what this table is really trying to tell you. And it's really trying to tell you some very interesting things about what it is that makes certain conformal field theories holographic or certain states dual to semi-classical geometries. But for our purposes today, what's really important in this table is specifically these free entries. These are free entries these are free necessary conditions on entropies if the Ryuta-Kayanagi formula is valid. And I just want to tell you that notice we have AB and A on the other side, AC and C on the other side, BC and B on the other side. The combination AB minus A plus BC minus B plus CA minus C is exactly the combination that we have seen over here, where the regions are labeled. Do we see this combination? And the answer is yes. Here, number 4 contains precisely the same combination there. And so when you look at these expressions, what you really should be seeing is a discrete version of differential entropy is greater than or equal to something. That's what these inequalities are saying. This one I put in dotted lines because it's actually equivalent to this one, just the regions are relabeled. For some technical reason, this is presented as a separate inequality, but it actually has the same content really. And so each of these three things is really a version of differential entropy. So now what I'm going to do is what I want to tell you about is that my research group have found a generalization of these types of inequalities, and it's an infinite generalization. And we call this infinite generalization the toric inequalities. So here they are. And here, unfortunately, I have to ask you for to understand just a modicum of notation. So imagine that you have a bunch of regions called A1, A2, A3, and so on, up to M, and a bunch of regions B1, B2 through Bn. And these regions together are in a pure state. We have found that under these assumptions, if Ryuta-Kayanagi holds, then this inequality is valid. Okay. Now, here I have to ask you to understand the notation for it. We have these regions A1, A2, A3, A4. I denote with AIK the set of K consecutively labeled regions that start with I, with the ith region. And then there's the same notation for B. Further on, I will assume that the number of A regions and the number of B regions is odd. If that number of A regions and B regions is odd, then it makes sense to talk about the just larger than half and just smaller than half number of terms, the smallest consecutive majority and the largest consecutive minority of A regions and B regions. And these things are denoted with AI plus minus, plus for majority, minus for minority. And there's the same notation for the B. So with this notation, we are now ready to understand what this thing is really, what this thing really means. Now, to give you a sense of what this means, let me give you an example. Oh, and yeah, we're going to ignore that. So here's an example. I suppose that I have 5 A regions and 3 B regions. I have the entropies of the consecutive majorities of A regions. For 5 regions, a consecutive majority would contain 3 regions, such as A1, A2, A3, or A3, A4, A5, or A5, A1, A2. And then on the B side, I have largest possible minorities. What's the largest possible minority out of 3 regions? It's just 1 region. And so here I have all possible combinations of 3 consecutive A's and 1 consecutive B. And on this side, I have 2 consecutive A's and 1 consecutive B. Now, what would happen if there were no B's in the picture? This thing would literally be like our discretization of differential entropy. I would have A1, A2, A3 minus A1, A2, or with A1, A2 on the other side. A3, A4, A5, and then A3, A4 on the other side. So what this thing is just like this discrete version of the differential entropy formula that we saw before, but it's made a little more complicated because it contains information both from the A side and from the B side. This is what I mean by a two-sided structure. Okay, so we go back to the table of all known holographic entropy inequalities, and here are the 3 that we saw before. These things are direct generalizations of differential entropy as we knew it before. And now I want to tell you that these new inequalities we had discovered, the ones that we had seen on the previous 2 slides, happen to include these 2 ones as well. So they don't include everything in this table, but they include some part of this table. And I want to say that just like if you took a continuum limit of the red things and you would discover the old differential entropy, when you take a continuum limit of these blue things, the new inequalities, then we will get just the Crofton formula that we want. So my task for the next 20 minutes is to tell you in more detail about how this happens. Are there any questions? So if there are no questions, then I will, but I do encourage questions, and please do interrupt me. Okay. So the next thing I want to tell you is that these inequalities, there's some interesting structure about these inequalities, one that I am infinitely excited about, and I want to share some of that excitement with you. So these inequalities naturally live on a tessellation of the torus. You could see that the torus might be relevant right away because remember we had these A regions and B regions and they are cyclically ordered. And then we're summing over all possible sort of starting points for our consecutive k-tuples of A regions and B regions. So by the time we add up all the initial points for the A regions, that's one circle. I add up all the B regions, that's another circle. I'm really doing something on a discretization of two circles. So that's a discrete version of a two torus. The correct way of thinking about this torus, or the most fruitful way of thinking about this torus, is given in this diagram here. And the way this diagram works is that I have taken every term which lives on the greater than side of this entropic condition. Again, I remind you, these are conditions for Ryuta-Kayanagi to be sensible. So necessary conditions for that. So I take every entropy, every region which appears on the greater than side of that inequality, and I represent it as a face. And I take every region that shows up on the less than side of the inequality, and I represent it as a vertex or as a node in a certain tessellation. And the idea is that by the time, what's kind of amazing about this inequality is that when I apply these rules, then I find that every left-hand side term, so every face is, well, okay, I'll say this in a moment. And so this is the rule for how to represent, so far, this is the rule for how to represent the inequality on a lattice. Okay. Now, the next thing I have to tell you is about which faces are and which vertices are incident. Yes, so far I just told you faces are left-hand side terms, vertices are right-hand side terms, but how do I know which vertex is attached to which face? And so the statement is that a vertex or a node is incident to a face if and only if the regions that they represent do not cross. And do not cross is another way for saying one is a subset of the other, or they are disjoint. That means no crossing. So you could see that there is a reason why it's useful to have a concept of non-crossing. One is contained inside the other is one possibility. The other possibility is that they should be disjoint. But if they're disjoint, that means that one region is contained in the complement of the other. So one way or the other, there is some containment going on. Let's test what this means by looking at this picture. Let's look at A4, A5, B3. It's a subset of A3, A4, A5, B3. So this is why this vertex is incident to this face. It's a subset of A4, A5, A1, B3. So that's why this is this vertex is incident to this face. A4, A5, B3 has no overlap with A1, A2, A3, B1. So that's why it's also incident to that face. And so this is the way that we decide which vertex is next to which face. You might ask, okay, so you designed a lattice based on which regions are non-crossing, yes, but why is this relevant or why is it important? The non-crossing is important because it's a necessary condition for the entanglement wedge nesting theorem. And so let me just remind you quickly, in ADS-CFT and it's from qubit sort of development, a key result is subregion duality, which is that if I have access to an interval in the CFT, or so in a subset of a CFT, then I have access to a definite subregion of the bulk geometry called the entanglement wedge. Now, it cannot, and the boundary of the entanglement wedge is the Ryuta-Kayanagi surface itself. So here is a statement which should make sense to everyone. Suppose that I give you access to some larger region, and then I take away the access of part of it, to access to a part of it. That's like going from a larger region to a smaller region, yes? It cannot be that taking away access to some information in the CFT increases my ability to decode the bulk. So this picture, which would represent the Ryuta-Kayanagi surfaces, cannot happen. It cannot be that when I go from a larger region Y to a smaller region X, my Ryuta-Kayanagi surface sort of bulges more and revealing or giving me access, granting me access to an extra region. That cannot happen. And so a theorem that guards this is called the entanglement wedge nesting theorem. And it precisely applies when I have a pair of regions that do not cross. So every time you have a face and a vertex next to each other, it's really a statement about I can use the entanglement wedge nesting theorem in there. There's one more thing I want to say.
May I ask a question? But there is this additional term there in this inequality, the term on the right, that the SA1M term, that is not represented here in this lattice picture.
It's not represented here. And what I want to tell you is that these terms here, so like we see it on this lattice, the terms in the sums, but not this term, yes? They form this lattice. And the idea is that this term here is a topological bonus that I get because this lattice lives on a compact manifold. That's the statement that I will eventually build up to. So it's on a different footing because I built a lattice out of these entropies, and then because the lattice lives on a compact space, therefore, only due to the Ryuta-Kayanagi formula, there is a topological bonus due to the lattice being compact. That's what I will eventually tell you. So this term doesn't represent a vertex, doesn't represent a node, it doesn't represent a face. It represents a topological bonus out of the fact that these things formed a compact lattice. That's what I will tell you in a moment. Okay. All right. But remember, the differential entropy-like terms are the ones that are differences of this and that. Yes, this was never the differential entropy. This one is like the statement that this is on a different footing. Combine these into a differential entropy-like term, and we have a statement differential entropy is greater than the entropy of all the A regions. That's like the entropy of a black hole, which has an A side and a B side. Okay, so the next thing I wanted to, returning to the previous line of thought, so the next thing I want to tell you is that about this graph. So far, I introduced a graph. The graph tells me about these terms, but not about the last term, just like the question a moment ago. And so far, I told you about this graph or about this lattice in terms of the faces and the vertices. But you would say to me, you might say to me, in graph theory, we don't construct graphs by giving me vertices and faces. You give me vertices and edges. And faces are derived terms after I decide what kind of geometry my graph lives on, is embeddable on. But here we're starting from the faces. So at the very least, we should understand what are edges. And so here is a statement. Edges are instances of conditional mutual information. So to explain this point, I have drawn a specific edge here. And that specific edge, yes, is first of all, it has two faces next to it. That means two terms which live on the left-hand side. Specifically, I wrote them as A1, A2, B2. That's this one. A1, A2, A3, B2, and A3, A4, B5. Sorry, you can read this thing. So there it is. And then minus the two vertices, which are the endpoints of the edge. These are negative terms. They're terms that live on the other side. So there this is. And so these four terms are the terms that are directly related to the edge. Now, these terms this doesn't look like a conditional mutual information yet, but I remind you that we're working in the context of a pure state. So that means that I can trade any term into the complementary region, which has the same entropy. So I'm going to not touch this term and this term, but I'm going to trade this term for the complement. That gives me A1, A2, B2, B1. And I'm going to trade this term for its complement. That's A1, A2, B2, A3, B1. And now when I write this combination, you see that this combination has a structure, which is like X, Y, X, Z minus X minus X, Y, Z. And that's exactly what shows up in the definition of a conditional mutual information. And so basically every edge here is associated with a conditional mutual information of some two individual little regions conditioned on a third big region. Now, conditional mutual information is famously non-negative, and that's known as the strong subadditivity inequality. And so if I just added up all of these edges, I would know that the combination of them is already non-negative. So I could combine all of the terms that live in the sums, and I say that's a sum of some conditional mutual informations greater than or equal to 0. Now, crucially, my inequality has an extra term that was just asked about. And that extra term is there on the right-hand side. It's an improvement over strong subadditivity. So the idea is that and this improvement is only there because we assume the Ryuta-Kayanagi proposal. Without the Ryuta-Kayanagi proposal, all we could say is that I have a bunch of conditional mutual informations. They're definitely non-zero because strong subadditivity. But now I say that they are greater than or equal to, collectively, those conditional mutual informations, not just greater than or equal to 0, but greater than or equal to some other quantity, which is itself greater than or equal to 0. That's the improvement. And that improvement is exactly that one extra term. All right, are there any questions or comments? Okay, so I'm building up towards the differential entropy connection, which is the main subject of this talk. We're kind of ready to do it. So what I'm going to do now is I'm going to take this expression over here, and I'm going to study it in a context where I have a pure state living on many AIs and many BJs, but I want to place these things on two circles, just like we wanted to in the, making contact with the previous discussion of differential entropy. So I consider as an entangled state on two CFTs that live on two circles, and each CFT is divided, each circle is divided into regions A1, A2, A3, and A4, and so on, and B1, B2, B3, and so on. Okay, they're in some entangled state, and if they're holographic CFTs, then the entanglement forms a wormhole, and we are talking here about a two-sided black hole. The dotted thing, which you see here, is the entropy of the A terms. That's the entropy of all the A regions. That's exactly the value of this last term, which on the previous slide I advertised as a topological improvement. But from this point of view, this is not a topological improvement. It's just the entropy of the two-sided black hole. Okay. All right. Now, I'm going to, for the purpose of presentation, I'm going to redraw this picture, this two-sided trumpet in this form. I hope you can see why. This is topologically an annulus. So in this redrawing, the dotted curve doesn't look like it's the smallest curve, but we have to remember that geometrically it actually is the shortest possible curve that divides A from B. Okay. And then what we want to do now is look at any term, such as the entropy of this AI plus region and BJ minus region, which we defined before, which show up in the inequalities. Well, the AI plus region, any one of them, is something which is just larger than half of the A circle. And the BJ minus is something that is just smaller than half of the B circle, right? What could the entropy holographically of such a term thing? Well, it can be in one of several phases. One phase is and I drew them for you here. So one phase is a phase which I drew it in red here. Oh, okay. So this is a little, this is not a perfect picture, and sorry about that. But one possible phase for the holographic entanglement entropy here is that I could have a geodesic that just subtends the A part and just subtends the B part. This is one potential phase here. The other potential phase is the thing that subtends just the complement of B and just the complement of A. That's the other phase. So unfortunately, this picture is wrongly colored. These two things should be both of one color, and these two things should be both of one color. And I apologize for that. Another option for what the RT surface could be is that they could be these intervals could be in a sort of connected phase where there is a geodesic that connects this endpoint of A to this endpoint of B and this endpoint of B to this endpoint of A. So I have a few phases here that are possible as realizations of the Rita Kayanagi proposal, and which one actually is realized depends on which one has the smallest combined length, so which one is minimum. Okay. So now what I want to tell you is that remember, we have recast our inequality in the form that I have a sum over these conditional mutual informations, which correspond to the edges in the lattice. Each of them looks like this. Now imagine that I have infinitely many A's and B's. So I don't just have 3 A's or 5 A's or 7 A's, but I actually take the continuum limit when I have infinitely many A's and infinitely many B's. This is just like the limit that previously would have given me back the differential entropy formula from those discrete inequalities that the holographic entropy cone program had independently discovered before. So previously, I knew how to go from those to differential entropy, and the correct procedure would have been to take the limit of infinitely many regions. Let's take the limit of infinitely many regions again. So in the continuum, this combination, which is a conditional mutual information, it's a basic constituent of what happens on our lattice that we saw before, becomes this guy. This is the second derivative of the entanglement entropy of a union of two intervals which have endpoints UAVA and UBVB. And it's this specific partial derivative. And now what I want to tell you is that this quantity it vanishes in every phase. We saw a moment ago that various phases are possible, but it vanishes in every possible phase individually. Why is this true? Well, so here I labeled for you the endpoints UA, VA, and UB, VB. And depending on which phase we're in, you will notice that the entanglement entropy is like the length of this geodesic plus the length of this geodesic. That something depends on UAVA and UBVB. Or if I go the other way around, it also depends on UAVA, UBVB. Or possibly it depends on UA and UB and VAVB together if I'm in this connected phase. But no matter what, I do not have a term that depends on VA and UB simultaneously. And so these conditional mutual informations that I am adding up to when I evaluate this quantity, they're actually all vanishing in every phase, because none of these combinations of geodesics has any joint dependence of VA and UB, regardless of which phase I'm in. So are all of these conditional mutual informations zero? Is this inequality even right? Well, there is one catch. The catch is that it might be non-zero if my regions that I'm looking at are just on the phase transition. The argument that says the entropy has this form, therefore this quantity vanishes, it relies on me being in one phase. But if I'm just on the border of two phases, just at the locus of phase transition, this argument does not apply. And that's when all the conditional mutual informations that are non-vanishing, that's when they exist. And so I have the conclusion that the only non-zero edges in our graph live on the on the locus of phase transition. Okay, so now we are ready to take the continuum limit of our inequality and study it properly. When I take the continuum limit of our inequality, I get an expression of the form like this. This is the continuum version of this double sum that I have over here. This is the integrand that I said before. And now I remind you of what happened on the previous slide. These things this integrand is almost always zero. It's only non-zero on the phase transitions between different phases. And if I'm on the border of two different phases, then that's a codimension one condition. So the integral will actually localize onto a codimension one locus, which is the locus of phase transition. It turns out my students, and especially Zhang Dachan, have showed this. It turns out that this locus miraculously always wraps a cycle of one of our torus. This is not easy to see, and it's completely impossible to see in the continuum. So this is actually like an infrared statement that in the continuum is very hard to see. It's covered in this UV junk. Only by going to this discrete picture of that we used in the inequalities, only then it becomes kind of manifest why that's true. Well, so this is an interesting fact about this locus of the phase transition. It's always non-trivially wrapped on this torus. Regardless of that, this larger two-dimensional integral always localizes onto the locus of phase transition. It's a codimension one locus. Therefore, it really becomes a single-dimensional integral, which turns out to simplify in this fashion. And then we say, that's actually differential entropy. And so this guy equals a differential entropy. And therefore, this is just the two-sided Crofton formula that we wanted. It's a two-sided integral that when you evaluate it, it computes a differential entropy for us. So success. On the previous slide, I showed you I said that the integral always localizes onto a codimension one locus. So in other words, almost all the edges are vanishing, but only a codimension one set of edges is non-vanishing. So here's an example I prepared for you. In this context, suppose that the region B free is smaller than on the others. Then all of these edges, like this one and this one and this one, are vanishing. only these edges, these conditional mutual informations are non-vanishing, and you can see that the cycle that these edges together make up a cycle which is non-trivially wrapped on the torus. If you evaluate the expression along, like integrating along this direction, then you get a differential entropy, which is just what we wanted. You might still ask me, what is this a differential entropy of? And here is a picture. This differential entropy is the differential entropy for a curve which is tangent to all the geodesics which are just at the phase transition. And so if I drew a set of all combinations of A regions and B regions which are just on the phase transition, that's where the integral, our two-dimensional integral, localizes. Then together, these things will have a common envelope. And that common envelope, I drew it here as a purple curve. That common envelope is always larger than the horizon of the black hole, because the horizon of the black hole is the smallest possible curve. And that's the geometric meaning of this inequality. And so that's the differential entropy that we have been computing using our Crofton formula. Okay, so here are some other interesting facts about this thing. I already told you that the integral localizes on codimension 1 cycles on the torus. It always localizes on loops. The loops are loci of phase transitions. It turns out that there is always a loop with wrapping numbers which are combinations of 1, 1, and 1 minus 1 in terms of the wrapping numbers of the torus. And basically the 1, 1 and the 1 minus 1 loops have the interpretation of evaluating one differential entropy quantity on the A side and on the B side. So whether your cycle wraps a 1, 1 or the 1 minus 1 cycle tells you about whether the curve for which you are computing the differential entropy resides on the A side or on the B side. So these are some other facts which I don't have the time to tell you in detail, but I hope that I have piqued your interest, and please check out our previous and the upcoming paper. We have found, to summarize, we have found a two-dimensional version of, a two-sided version of the differential of the Crofton formula, and really of differential entropy at the same time, which does not worry about the horizon. And in fact, it makes enthusiastic use of the fact that there is a second side cloaked behind the horizon. So thank you very much for your attention. This is it.
Thanks very much, Bart.